Okay, so in our implementation of the employee class and the derived manager class, we simply inherited the employee print function and used that to print a manager. But we may prefer to override the behavior of the manager print function by defining print within the manager class itself. When I then invoke print on a manager object, the manager class's print function will be called, whereas when I invoke print on an employee object, the employee class's print function will be invoked. So here we have added in our manager class definition a print member function declaration that's identical to the employee print function declaration, and in the manager.code file we have added the definition of the print function that belongs to the manager class. We are using the employee print function within the implementation of the manager print function by simply prefixing the print call with employee : : Okay, so we print the string manager information, then we print the employee part within the manager, then we also display the title and the budget for the manager. Here on slide 16, we have the bottom part of our previous main function. All of the code in the application is identical to what we had before. However, when we recompile and link with the modified version of the manager class implementation, now when we invoke the print member function on Carl, since Carl is a manager object, manager : print is going to be called. And when that happens, we get these 4 lines of output for Carl rather than just the 1 line of output for Carl that we had previously when we were relying on the employee class print function. A manager is a kind of employee, and therefore it turns out that we can use a pointer to employee to point to a manager, and we can invoke through that pointer to employee any member function that's valid for the employee class. Similarly, we can do the same kind of thing by using a reference to employee to refer to a manager. All right, so here we're adding a little bit of code at the end of our main function. We're saying P is a pointer to employee, initialized to point to the employee object Alex, and when I call P arrow print, that displays information about Alex. Now I'm going to modify P to contain the address of the Carl object and invoke P arrow print to display Carl. Let's think about what we would like to have happen, and let's see what actually does happen in this case. If I have a pointer to an employee pointing at Alex, and I say print Alex, P arrow print, then Alex is an employee, and I expect the employee print function to be called to display Alex. If I make P point at Carl, so P contains the address of Carl, and I call P arrow print, probably I would like the program to figure out that P is now actually pointing at a manager, and even though a manager is a kind of employee, I would really like to have the manager's print function called. But in fact, what does actually happen is that I do get the employee print function called for Alex, and I also get the employee print function called for Carl, even though Carl is a manager. Technically speaking, that's okay, and we know that the employee print function will work fine for Carl because Carl is a kind of employee. But let's see what we need to do in order to get the correct print function to call looked up depending on whether P is actually pointing at an employee or whether P is actually pointing at a manager. It turns out all we need to do is to add the keyword virtual to the declaration of the print function in the base class. Okay, so if the base class member function is declared to be virtual, that means when I invoke this print function through a pointer to employee or a reference to employee, I should actually look up at runtime to see whether that pointer is truly pointing to an employee or instead pointing to a manager. And if the pointer is pointing to a manager, I should call the manager print function instead. All right, so all we've added is this one keyword, virtual, in the declaration of the print function. The implementation of the employee class actually does not change at all. All right, so here we have the employee.cpp file. The print function is identical to what we already had. We don't have to add the virtual keyword in here anywhere. Furthermore, we don't make any change to the manager class either in the definition in the header or in the code file in the .cpp. And now, when I run this same bit of code, P is a pointer to an employee, initialized to contain the address of Alex. P arrow print calls the employee print function. And if I change P to contain the address of Carl, who is a manager, and I invoke P arrow print, now we get the manager print function. All right, so here's the output that we get. For the green P arrow print, where P is pointing at an employee object, we get the employee : print function. But for the blue one, where P is actually pointing at a manager object, we get the manager print function called instead. Okay, so in summary, when you put the virtual keyword in front of a member function declaration in the base class, that means to the compiler that any time an object is accessed using a pointer to a base class or using a reference to a base class, the correct function to call should be looked up at runtime. It's completely reasonable to ask, well, why doesn't this always happen? Why do we have to add this keyword virtual in order to get this behavior that makes sense? And the answer is that looking up something at runtime takes a little bit longer than making the decision in advance at compile time. And one of Strustrup's design criteria for the C++ language is that whenever possible, C++ should be just as fast as C. If you have to choose between speed and safety, for example, by doing runtime bounds checking on arrays, you choose speed over safety. Likewise, if there's a trade-off between speed and convenience, in the case of hard coding a decision to call the employee print function versus making a decision at runtime to call either the employee print or the manager print, the default behavior is to go with the fast implementation of hard coding employee print. So it's left to the developer of the class to decide which function should be declared virtual so that you get this runtime lookup, you get this more flexible behavior, but there is a slight performance cost to doing that. If you are willing to pay the performance penalty, you have to ask for it, is basically the thinking. Now, here on slide 24, we're showing a modification to the manager class definition in which we're adding the virtual keyword to the print declaration here. Many people do this. It's not strictly necessary. Once a function has been declared virtual in the base class, that virtualness will be inherited at all of the derived class levels. Okay, so it's perfectly fine to add virtual in the manager class, but it's not necessary. Now, internally, what enables the program to look up at runtime which version of print to call is usually something called a Vtable. And I'm not going to read through all this detail on slide 25, but basically the idea of a Vtable is it provides a table of function addresses that the program can look at to figure out at runtime which of several available functions should be called. Here's a diagram on slide 26. Okay, so if an object has a virtual function, then the usual way that this is implemented is to provide something called a Vtable pointer, pointing to a table of the available virtual functions. For the employee class, there's only one virtual function, which is the employee print function. And the same is true for the manager class. In the manager class, we're simply inheriting the fact that print is virtual. We have provided an override of print within the manager class. So the Vtable internally within the manager object points to its own table, which starts with the manager print function. So given this arrangement, if I have a pointer to an employee, and I say I want to print the current object, we follow the pointer to the employee part of the current object, and we look up the first function in the Vtable, which is how to print the current object. If we have an employee pointer pointing at a manager, well, a manager contains within it an employee, so we follow that pointer and look up the Vtable for the employee part of that manager, and follow that Vtable pointer and invoke the first function in that Vtable. So we end up invoking the manager print function. Okay, so by making this function virtual in the base class, we cause runtime lookup to occur whenever we're accessing an object through that base class pointer or through a base class reference. And almost always this gives us the behavior that we want. If we have, for example, a list of employees, and in that list we're keeping track of pointers to dynamically allocated employee objects, if we step through that list and say, okay, I want to print each one of these, well, in the case where the list item is pointing at a manager object, we want to have the manager print function called. Otherwise, we want to have the employee print function called. Now, this raises a sort of inverse question as well, which is, what if I do have a collection, like a list of employees and managers, and I'm using a pointer to employee to step through these elements, but when I'm pointing to a manager, I want to invoke the employee print function. That is, I always want to invoke the employee print function regardless of whether I'm actually pointing at an employee or actually pointing at a manager. How can I arrange that? Well, it turns out that you can prefix the print function with the member of operator and the employee class name. So here, I've declared this variable p2, which is a pointer to employee. Initially, p2 contains the address of Alex. Alex is actually an employee. And if I say p2 arrow employee : print, that's going to force a call of the employee class's print function on Alice. When I change p2 to contain the address of Carl, of course Carl is a manager, but if I invoke p2 arrow employee : print, that is still going to invoke the employee class's print function on Carl. I could do the same thing directly by accessing Carl and using a dot to invoke a particular member function. In this case, I'm saying employee : print rather than just plain print. If I said Carl.print, that would invoke the manager print function, but if I say Carl.employee : print, that's going to invoke the employee print function. And so here we have the output of the code on slide 27. We have Alex displayed as an employee, which Alex is, and we also have Carl being displayed as an employee, first through the pointer p2, and then by directly using Carl with the dot. Okay, so that gets us to the end of lecture 17, our introduction to inheritance, including this important idea of virtual functions that are looked up at runtime rather than hardwired at compile time.